Welcome back to the Savage Sullivan Math website. Today we're going to look at two more examples of elimination, but we're going to have an additional step to do. So with this one, when we look, we could solve this system by substitution. It wouldn't be terribly hard to isolate the y here, but it's set up pretty nice for elimination as well with an additional step. So upon observing the system, I am inclined to want to eliminate the y's. And the reason why is because I really only would have to multiply one equation. If I wanted to eliminate the x's, I would have to multiply both. What's nicely set up too is that the signs are different, which tells me I could eliminate by addition, which is always kind of my default method so that we don't make silly sallies with signs. So I'm going to take the top equation, and because I want to eliminate the y's, I want to get this to be a -3 so that I could add to eliminate, which would mean I have to multiply this by 3. We have to be careful that we remember to multiply the constant on the end too. So when I rewrite this up here, I'm going to have 6x minus 3y equals 12. Remembering to distribute to all of these numbers. And just because I like to have them written on top of each other, I'm going to recopy the other equation here. Now we have a system that's set up nicely for elimination. So I'm going to go ahead and I'm going to add these two equations together. 6x plus 7x is 13x. These two, -3y plus 3y, should eliminate. That was my goal. And again, remembering to add the constants, 12 plus 27 is 39. Again, we have a nice one-step equation. Divide both sides by 13. And hooray, we get x equals 3. Now, once again, you get a choice of which equation you want to plug into. But really, I'm going to go back and plug into my original equations over here. So I'm going to plug into the bottom one down here. Again, you could choose. You could plug into the top one if you'd like. So I'm going to take this 3 and I'm going to replace it for the x here. So I'm going to have 7 times 3 plus 3y equals 27. 7 times 3 is 21 plus 3y equals 27. Subtract the 21 from both sides. We get 3y equals 6. So y equals 2. So our point in question is 3, 2. We always want to do a check, especially when there's extra work involved. And when we check, it is nice to use our original equations to make sure that we didn't make a mistake anywhere in the problem. So off to the side, I'm going to go ahead and I'm going to do a check. And remembering that we have to check both equations in the system, I'm going to start with the top one. Where I see an x, I'm going to plug in 3. Where I see a y, I'm going to plug in 2. 6 minus 2 gives me 4. And yes, it works. But again, having to check the bottom one. So again, where the x is, we're going to plug in 3. Where the y is, we're going to plug in 2. And if we did it correctly, it should be 27. 21 plus 6 is in fact 27. So yes, we have our solution point.
Just like Mrs. Savage said, when you have a system of equations, you could solve it any way. We could change this to slope-intercept form and easily graph it. We could solve one of these equations for a particular variable and use substitution. That would be fine too. But in this particular case, this is set up nicely for elimination because all of the terms are aligned. The x terms are aligned, the y terms are aligned, the equal sign, and the plain old constant. But the problem is, just like the last problem, the coefficients do not match. So it's my job to make sure that the coefficients do match. I have to multiply both equations in this particular case because there is not one number I could multiply 7 by to get to 8, and the same with 2 to get to 3. So I'm going to multiply both of the equations so I can get the coefficients to match. I'm going to try to eliminate the y's, only because I like working with smaller numbers. And the least common multiple of 3 and 2 is a 6. So I'm going to make sure that this 3 becomes a 6. So to do that, I'm going to multiply the top equation by 2. So this becomes 16x plus 6y is equal to -14. And I need to make this 2 become a 6, so I need to multiply the whole bottom equation by a 3. So the bottom equation becomes 21x plus 6y is equal to a negative 9. Now if you notice, now the coefficients on my y's match, and they are both positive. And I want to eliminate those, which means I need to do an operation that will make the y's become 0. So 6 plus 6, that doesn't get rid of them. 6 minus 6 is 0, so I need to subtract this equation. So I am going to do 16x minus 21x, which is negative 5x. 6 minus 6 is 0. That was our goal. Negative 14 minus a negative 9. That's the same thing as saying negative 14 plus 9, so that equals a negative 5. Divide both sides by negative 5, and you get x is equal to 1. Plug that 1 value into one of your equations. You technically have 4 to choose from. I would choose one of the originals just because the numbers are a little bit smaller. So I'm going to choose the bottom equation. Instead of x, I'm going to plug a 1 in, and then I have the 2y is equal to negative 3. So 7 plus 2y is equal to negative 3. Subtract 7 from both sides. I have 2y is equal to negative 10. Divide everything by 2. Y is equal to negative 5. I believe my answer is 1 comma negative 5, but I need to do the check to be certain. Again, you have 4 different equations that you could plug in your values for x and y into, but I would recommend plugging it into the original equations, because what happens if you had made a calculation error? Then you wouldn't even know you had the wrong answer. So always use the original equations. So for the top one, 8 times my x value of 1 plus 3 times my x value of negative 5 is equal to negative 7. 8 minus 15 is equal to negative 7, and negative 7 is equal to negative 7. All right. Second equation, 7 times 1 for x plus 2 times negative 5 for y is equal to a negative 3. So 7 minus 10 is equal to negative 3. Negative 3 is equal to negative 3. Nice, we got it. So here is our final answer. If you found this video helpful, please like and subscribe.